Hello everyone. My name is Hai Huang, and I'm presenting our paper, Open-Set Cross-Modal Generalization via Multimodal Unified Representation, from Zhejiang University. Our work tackles a fundamental challenge in multimodal AI, how to generalize not only across modalities, but also to unseen categories, a setting we call Open-Set Cross-Modal Generalization, or OSCMG. Let's begin by situating OSCMG in the context of prior research. Domain generalization, DG, aims to transfer to unseen domains, but only in single modalities. Multimodal DG, MMDG, extends this to multiple modalities, but still assumes closed sets of classes. Cross-modal generalization, CMG, focuses on transferring knowledge between modalities, but assumes that the label space is consistent across training and testing. Open-set DG, OSDG, allows unseen categories, but only within a single modality. Now, real-world multimodal scenarios combine both challenges. We need to transfer knowledge across modalities. We must also generalize to unseen categories that were not part of training. This is exactly what OSCMG is designed to evaluate. In OSCMG, the source modality has a smaller set of classes, and the target modality contains additional unseen classes. For example, training on video-audio pairs with dogs and cats, but testing on a modality that also includes elephants. This setting reflects practical applications, where unseen categories and new modalities naturally appear. By defining OSCMG, we create a more realistic and challenging benchmark for multimodal unified representations. Part 2, Fine-Coarse Masked Multimodal Info NCE. To address OSCMG, we propose a new architecture called MICU, which includes two major components. The first is Fine-Coarse Masked Multimodal Info NCE, FCMI. Traditional multimodal contrastive learning methods often emphasize coarse global alignment, for example, averaging features and aligning across modalities. While effective, they overlook fine-grained temporal and structural relationships. Our FCMI improves this by combining coarse-grained masked contrastive learning, aligns global semantic features across samples and modalities. Fine-grained masked contrastive learning operates at the block or time step level, aligning detailed features within samples. Importantly, we use masking strategies to increase robustness. By masking the same positions across paired modalities, the model learns to focus on consistent semantic regions, rather than superficial modality-specific cues. If you look at our poster's visualization of the representation space, you'll see that FCMI produces tighter alignment across modalities and sharper separation between known and unknown categories compared to prior methods. Part 3, Cross-Modal Unified Jigsaw Puzzles. The second core component of MICU is the Cross-Modal Unified Jigsaw Puzzle, CUJP. The idea comes from self-supervised learning. Jigsaw puzzles have long been used to encourage spatial reasoning in vision models. Prior works extended this to single-modal puzzles or multimodal puzzles, but these still carried modality-specific biases. Our CUJP innovates in three ways: unified, modality-agnostic puzzles. We shuffle blocks of discrete representations drawn from any modality, treating them as if they come from a single shared modality. Block-level alignment. This forces the model to achieve finer-grained consistency within the unified space, beyond global sample-level matching. Efficiency. Unlike previous multimodal jigsaw methods, e.g. MMJP, which require factorially many permutations across all modalities, CUJP reduces the complexity drastically. For example, with 3 modalities and 4 splits each, MMJP needs nearly 500 million computations, while CUJP only needs 24. The results are significant. CUJP improves feature diversity, enhances open-set robustness, and provides a much more efficient self-supervised signal. To summarize, we introduce OSCMG, the first benchmark task to test both cross-modal transfer and open-set recognition. We propose MICU, integrating fine-coarse masked info NCE for robust alignment and cross-modal unified jigsaw puzzles for modality-agnostic fine-grained learning. Our approach achieves state-of-the-art results on both OSCMG and existing CMG benchmarks, showing superior performance across multiple datasets. By addressing the dual challenge of unseen modalities and unseen categories, OSCMG and MICU bring multimodal generalization one step closer to real-world applicability. Thank you for your attention.